Good morning, students. So this is the second lecture and last lecture of chapter 4. If you remember, in chapter 4, we are talking about moments. Whenever a force is trying to create some rotation in a body or a particle, we have moment. So moment is linked with rotation, or you can say that they are interrelated. All right, so first topic of today's lecture, moment of a couple. Right? We already talked about moment, that how we determine moment, how we find out moment, force times the moment arm, which is the perpendicular distance between the line of action of the force and that point, right? So that's how we find out moment, we calculate moment, okay? All right, so now we are going over moment of a couple, right? What are the objectives of this, this topic? Define a couple, determine the moment of a couple. Okay, so first of all, what is a couple? So if you see these two pictures on your screen, the picture on left side, so what is this guy doing with his two hands? So he's trying to rotate this wheel, right? Rotate this wheel, we can find out with the direction of the forces that he's trying to create clockwise rotation in this wheel, right? So what is he doing? He's applying 30 newtons force, let's say, in this direction, okay? And with this hand, he's applying 30 newtons force in this direction. So the forces are in opposite direction, right? One is positive x direction, one is negative x direction, okay? So they are opposite, okay? And they are equal, 30 newtons, 30 newtons. So both forces are equal. Now, if you take sigma fx equals to 0, so 30 minus 30, we get a zero balance force, right? But if you see, even though the forces balance out each other or cancels out each other, there's some rotation going on, right? Why there is some rotation? Why there is this rotation of this wheel? Because of the couple, right? Because although these are equal forces and opposite forces, so they cancel out each other, but they have this distance, 0.4 meters, this perpendicular distance between them, right? So once we have two forces which are equal and opposite, right, and parallel to each other, and they have some distance between their line of action. So then these two forces are called a couple, right? And the moment created by these two forces or moment created by this couple is called moment of a couple, right? So we discussed what is a couple and we discussed moment of a couple, right? And we are going to learn the same in this topic. In the picture on the right, what is this guy doing? He is trying to rotate this steering wheel, right, with his two hands, applying this force in this direction and this force in this direction. Let's say these two forces are equal, right? So F equals F, okay? And they're opposite, as you can see, right? And they are parallel, okay? And they have some distance between them, right? This is the distance, perpendicular distance between these two forces. So that's a couple, right? And although, again, that these two forces are equal and opposite, but they're creating some moment, they're creating some rotation in this steering wheel, right? So that's how this moment of couple works, all right? So let's move forward. Okay, let's see here. A couple is defined as two parallel forces with the same magnitude but opposite in direction, separated by a perpendicular distance d, right? So this is the definition by the book, right? As we discussed the details in the earlier slide. So this is the book definition, A couple is defined as two parallel forces with the same magnitude but opposite in direction, separated by a perpendicular distance d. Right? So these all are the conditions to make these two forces or any two forces a couple. Right? So first one is two parallel forces. Right? That is the first condition. Okay. Same magnitude. This is second condition. Okay. Opposite in direction. This is third condition. Separated by a perpendicular distance d. This is the fourth condition. So once we have these four conditions met, then we say that it's a couple of forces, right? And whenever we have a couple, we have some type of moment. Okay. If you see here, this is force F in this direction, right? This direction. This is negative F because this is opposite to F. So let's call it negative F, and which means that they are equal and opposite, right? And they are parallel, as you can see. This is the direction of negative F, right? And they have some distance between them, perpendicular distance, right? Which is this guy, D. So this is a couple, right? There's a couple, and once we have a couple, then we have moment of a couple moment, right? So that's why we have this rotation. Okay, so that's how it works. Okay, the moment of a couple is defined as m sub o equals f times d, right? In scalar analysis, right? So f times d, f is the force. So we'll take the magnitude of the force. Both forces are equal, so we just take the magnitude of one force, and then d is the perpendicular distance between the two forces, line of action of two forces. But it has to be perpendicular distance, right? So that is the scalar analysis. Now, if you talk about vector analysis or moment in vector form, so we'll use this. M sub O equals R cross F. What is R? R is the position vector. If you see here in this diagram, this figure, what do we have? So this is one force. This is the opposite force, negative F, right? Let's say this is point A. This is point B. Okay. So what is the position vector? This is the position vector, right? Let's say RAB. Okay. So once you want to find out the moment of a couple in vector form, you'll take position vector cross product with the force vector. So R cross F will give you moment of a couple in vector form, right? Usually in 3 dimensions, 3D space. All right. R is any position vector from the line of action of the force, one force to the other force, right? Okay. So that was about some details of moment of a couple. Now let's see next what to have. The net external effect of a couple is that the net force equals to 0 and the magnitude of the net moment equals force times the perpendicular distance, right? We already talked about this, so no need to worry about this. Okay, we already discussed this. Okay, so that was the theory part. I hope that we got the concept, we learned the concept of how to say that, okay, these two forces make a couple, all right? And what do we have once we have a couple, right? So we have moment of a couple, right? Okay, now let's apply the same concept, same theory on some problems. Okay, so problem 1 of today's lecture. All right. So what is given? Two couples act on the beam with the geometry as shown. Okay. So on the left side of the screen, you can see this this beam, fixed beam with 1, 2, 3, and 4 forces acting on this beam, right, in different directions. Okay. So if you just take a closer look at these forces and their directions, so you can make out that there are these are two couples, right? So we have F here, we have negative F. So this F and negative F makes one couple, right? So because this F and negative F, they are equal, they're opposite, they're parallel, and they have 0.9 meters distance, perpendicular distance between their line of actions. Okay, so this is one couple. Now, if you look at these 2 kilonewton forces, two forces again, so this guy and this guy, right? So they are equal, they're opposite, they're parallel, and they have 0.3 meters as perpendicular distance between their line of actions. So that is couple number 2, right? So we have these two couples. Again, we need to make sure that we understand the concept, and we know how to apply that concept, right? Okay, so now we are applying the concept which we just learned. Okay, what do we need to find? The magnitude of F so that the resultant couple moment is 1.5 kilonewton meters clockwise. Okay, all right, so we need to find the magnitude of this force F, right? And the resultant couple moment is given. Okay, let's see how we do it. Add the two couples to find the resultant couple. Equate the net moment to the given moment, which is 1.5 kilonewton meters, right, clockwise, and we'll be able to find force F. Okay, so let's see, it's the same figure, and now let's find out the net moment. So what is the moment of the first couple, right, and the force F? Okay, so let's take force F times the distance d, which is 0.9 meters, right? So this guy, F times 0.9, right? F times 0.9 because it's a clockwise moment, right? It's creating a clockwise moment. Okay, this is creating a clockwise moment. All right, so this is the moment of the first couple, then the moment of the second couple, 2 times 0.3, right? And they are creating counterclockwise moment, right? Just assume the directions, just visualize and make out the directions. Okay, all right, so 2 times 0.3 is the moment of the second couple. Okay, and a positive sign because it's counterclockwise moment. Okay, so which gives you negative 0.9 F plus 0.6. Okay, so that is the net moment or total moment of these two couples. Now the net moment or total moment is already given in the statement, right, which is negative 1.5 kilonewton meter. So we'll just equate these two because both are the total moment. So this guy equals negative 0.9 F plus 0.6. Okay, so from here, just use your calculators and find out what is force F. Okay, so force F is 2.33 kilonewtons. Okay, so I hope you understand how we applied this concept, how we applied the concept of the couples and moment of a couple. Okay, okay, let's do another problem. Problem 2 of today's lecture. If you look at this figure, what's given? There's some kind of pipe assembly fixed at point O, and there are two forces, FA and FB, right? 450 newtons force. Okay, and the problem is three-dimensional. We have x-axis, y-axis, and z-axis. Okay, all right. So the dimensions are given, so no need to worry about that. Now, if you consider these two forces, FA and FB, they are equal, right? 450 newtons each, and they are opposite, right? And they are parallel, and they have 0.4 meters perpendicular distance between their line of actions. So they create a couple. And we know that once there's a couple, there's a moment of a couple, right? So what do we need to find? We need to find the couple moment in Cartesian vector notation. Since it's a 3D problem, we need to do, the vector analysis. Okay, vector analysis for couple moment. All right, so we already learned about how do we find moment in vector form. We need to take the cross product of position vector and the force vector, right? So we don't have a force in vector form. We'll need to find that force in vector form or Cartesian form, and we need to find the position vector r, right? So r cross f will give us the moment in Cartesian form or vector form. Okay. All right. So let's move forward. Okay. So let's take this guy, FB, right? FB equals 450 newtons. Okay, and this is the position vector, RAB. Okay, so we have RAB and we have force 450 newtons. Okay, so let's find out RAB first, since we know that RAB is in direction of the x-axis, right? So we don't have y component and z component in position vector. So what do we get as RAB? Just follow the tip minus tail rule. Here B is the tip, A is the tail. So what do we have? We'll get RAB equals 0.4 times I, and don't forget to put the units, meters. All right. Okay. So now we have the position vector. Now we want to find out force vector, right? Force vector. How do we find out force vector? You know that, right? We'll take on the components of this force F or FB and use IJK notations, right? All right. So if you look at this force FB, it's passing through x-axis, right? It's passing through x-axis. So what is the x component? There's no x component, right? So we'll have a 0I for x component. What is the y component? Just resolve this force FB into two components, right? So we will have y component and z component, right? So what is y component? 450 times 4 by 5. Right? So we'll have 450 times 4 by 5 times j. And it's a positive because it's in the positive y direction. Right? Then what is the z component? That is 450 times 3 by 5 times k. Right? This guy. And this is the negative component because this is acting in negative z direction. Right? Because this is your, sorry. This is your C component, and this is your Y component. Okay. All right. So just simplify this, and you'll get 0I plus 360J minus 270K. And of course, don't forget to put the units, newtons, forces in newtons. Okay. So now we have the position vector RAB. We have the force vector FB, and we can take the cross product to get the moment in vector form. Okay, and we know how to take the cross product. 3 by 3 determinant. First row is IJK, second row is position vector. So we only have 0.4, so 0.4, and next two entries are 0. Right. Then we have the third row, which is the force vector. So we'll have 0, 360, and negative 270. Right. Now just simplify that and expand this determinant. We know how to expand this determinant by now. Right. So just expand this determinant in this fashion. right? If you do that, what do you get? You get this guy, which is the moment vector, moment in vector form. 0i plus 108j plus 144k. And again, don't forget to write the units, because the units matters a lot, means a lot. Without these units, there's no meaning, right? In your test, in your homeworks, in your further work, in any of your courses, always remember to put the units, right? Because without units, there's no meaning. All right, so let's move forward. Let's do another problem. Problem 3. Now, if you look at this figure, there is some kind of structure, right? And this is point A, this is point B, okay. There are 1, 2, 3, and 4 forces acting on this structure, right? Okay, so we have 50-pound force here, 50-pound force here, 80-pound force here, 80-pound force here. Okay. So what is given in this statement? Let's read the statement. Two couples act on the beam with the geometry shown, and D equals 4 feet. Okay. So the perpendicular distance between the forces is given, right, as 4 feet. We need to find the resultant couple. Now, which are the two couples? If you look at the figure, so this 50-pound force, these two 50-pound forces, they are equal in magnitude, opposite in direction, and they are parallel, and they have this 4 feet perpendicular distance between them, right? So they make a couple. If you consider these two forces of 80 pounds, so they are equal in magnitude, opposite in direction, they are parallel forces, and they have this 4 feet perpendicular distance between them, right? So that's how we can say that we have these two couples acting on this structure. Now, let's come back to the requirement. We need to find the resultant couple, right? So we'll just need to find the resultant couple, okay? All right, so what steps shall we use to solve this problem? Step 1, resolve the forces in X and Y directions so they can be treated as couples. Okay, add these two couples to find the resultant couple. Okay. Okay, let's move forward. All right, so now we need to find the resultant couple. So if you look at the figure again, we don't have the perpendicular distance between these two forces, right? D is this distance. In the last slide, I think we made a mistake, so let's correct it here. So this is the distance D, right? This is the distance D from this point to this point, okay? All right, so now we don't have perpendicular distance between these forces. What we can do, we should resolve these forces into components, right? So let's say this guy, let's resolve it into X and Y components, right? X and Y components. These are X and Y components. Let's do this with this one. So this guy and this guy. All right. Okay. In fact, this guy is acting here, right? So that's All right. So now if you look at these forces again, so if you look at these blue forces, 50-pound forces, so which forces or which components are creating a couple or making a couple, right? So vertical forces, the Y forces or Y components are creating a couple because X forces, they do not have, or X components do not have any perpendicular distance between them, right? They are passing through each other. So that's why they are not creating a couple, okay? If you look at these 80-pound forces, so in this case, the X forces, they have some perpendicular distance between them, right? So they have this perpendicular distance between them. So these X forces, they are creating a couple, okay? And Y forces, Y components are passing through each other and they do not have any perpendicular distance between them, right? So they do not form a couple, right? And let's make this here. Makes more sense, right? Okay. All right. So now let's find out these components and then try to find out the resultant couple. Okay. So what is the X and Y component of this 50-pound force? 50 pounds cosine 30, right, which is 43.3 pounds, the Y component, vertically up, okay? And 50 pounds sine of 30, this guy, the X component, which is 25 pounds to the right, okay? All right, so we have these two components of this guy, this force, right here. Okay. So what you're going to do, both of these components form couples with their matching components of the other 50-pound force. We already discussed that they do not, right? Only the Y component of these two forces, they create a couple, not the X components. All right? Okay. This is the same thing, the 43.3 pounds, which is the Y component of this force, creates a couple. Okay? We already discussed about this. All right, let's move forward. Now resolve the lower 80-pound force, right? We already resolved that force, 80-pound force in the last slide. Now we have these two components, 80 pounds times 3 by 5. This is the Y component, right? Then 80 pounds times 4 by 5, acting to the right, or the X component, right? So now we have these X and Y components, and again, do both of these components create a couple with components of the other 80-pound force? No, the Y component does not create a couple, right? Only the X component creates a couple, okay? So now, since we know that there are two couples acting on this structure, we can find out the net moment, right? So let's find out the net moment. Now let's just draw the couple forces, right? So this is a couple here, right? Okay, so they have this distance d between them, right? So, and they're creating clockwise moment, right? So negative 43.3. No, it's counterclockwise moment. So let's take it positive. So 64 pounds times 4 feet, right? This guy. Now let's take 50-pound forces, and only the Y components create a couple, right? So this is one component, this is the other component. Okay, so how much is the distance? 3 feet is the distance d between them, right? So F times d, F is 43.3 pounds, distance is 3 feet. So just multiply that and take a negative sign because it's creating a clockwise moment, right? So this guy. Now just use your calculators and find out the answer. It will be 126 foot-pounds counterclockwise because it's a positive moment, right? So either you write positive 126 foot-pounds or you write 126 foot-pounds counterclockwise. Okay, so that's how we are done with this problem. Okay, so I hope by now we understand what is the couple of forces, what are the conditions when we say that, okay, these two forces create a couple, and what is moment of a couple, and how do we solve these kind of problems. All right, now next topic of today's lecture, reduction of a simple distributed loading. All right, what is the objective of today's topic? This topic, determining an equivalent force for a distributed load. Okay, so now first we need to understand what is a distributed load. Okay, now let's have a look at this picture. What do we have here? So there's a stack of boards, right? Maybe wooden boards or some kind of material, but this is the stack. This is the stack, and there is some kind of this storage rack here, right? This guy. So this stack of boards is placed or stored on this storage rack, right? So what is going on, right? What kind of load this stack of wooden boards applying on this storage rack, right? So the result is a distributed load, right, due to the weight of the wooden boards, and that distributed load is being applied on these storage beams or beams of this rack. Okay, so this is what we call a distributed load, right? Okay, to analyze the effect of this load on the beams, it is convenient to reduce this distributed load to a single force, right? Because it's always, complicated to deal with the distributed load. So what we do for the ease of analysis, we convert this distributed load into a single concentrated load, right? Single force, and we call it concentrated load, right? Okay. Now we'll see how we do it. Okay. So in many situations, a surface area of a body is subjected to a distributed load. Such forces are caused by winds, fluids, or the weight of the items on the body's surface. We already know that, right? If there's wind blowing against a wall, it creates it puts some force, it applies some force on that wall, right? So that's a distributed load because that's over a length, right? Similarly, the force applied by a fluid, or let's say if you again take the example which we discussed on the last slide, that if you stack something on a surface, on a beam, right, then it creates a distributed load on that beam, right? So that's how we have these distributed loadings in our real world, in our real life. Okay. The most common case of a distributed loading is a uniform load along one axis of a flat rectangular body. Okay, so let's say in case of a beam. Okay, so in such cases, W is a function of X and has units of force per length. Okay, so let's say this is a beam shown on the left side of the screen, right? This is the longitudinal direction or X direction, right? The length of the beam is L, right? Now, this loading shown with the help of these black arrows is the distributed loading. So let's talk about this distributed loading. The magnitude of this distributed load is W, right? And W is a function of X, because X is the direction along the length of the beam. Okay, now let's move forward and let's see how do we derive some equations. All right, so this is the beam, same beam again, with a length of L, right? And the longitudinal axis is X, and this is the W axis, or the magnitude of distributed loading. Okay, now consider an element of length dx. So let's take this small element, right? Let's take this small element. Let's take this small element with a length of dx, right? Now the force magnitude df acting on this element is given as this guy, right? So what is df? This is df, and df equals w times dx, right? So w is the magnitude times dx, which is the length of this element. Okay. All right. So now we want to find out what we are trying to do. We are trying to find out the resultant loading, right? Resultant load or resultant force, which can replace this distributed loading, right? So we are trying to find out this FR, resultant force, okay, which is at a distance of x bar from this point O, or the origin. Okay, so how do we do that? The net force on the beam is given by FR, and we'll just take the integral of dF, right? Integral of dF over the length. So again, just put in the value of this dF, right? dF here, so we'll have integral of Wx times dx, right, over the length. And we know that this is the area of this loading curve, right? So this guy, this is the area. Okay, so how do we find the resultant force? We just find out, if we can find out the area under the loading curve, right? That's the magnitude of the resultant force. Okay, now how to find out the location of the resultant force? Now once we have the FR, we can find out the location of the resultant force. So this is the same figure again. The force dF will produce a moment of x times dF about point O. So we are taking moment here at point O, and this small element which has a force of dF, it will create a moment of x times dF, right? Because this is the distance x, distance from point O to the element, right? And this is dF, the force. So dF times x, this will give us the moment, right? Now the total moment about point O, let's say this guy, mr, or resultant moment, is once you integrate x times dF over the length, right? Put in the value of dF, we'll get this integral of x times w of x times dx, right, over the length. Okay. Now assuming that FR acts at x bar, this guy here, so it will produce the moment about point O as x bar times FR, right? So this FR times x bar will give us the moment of the resultant force. Right? Just put in the value of FR here, we get x bar times integral of Wx times dx over the length. Okay. Now just equate these two, compare these two equations, right? Because both are the net moments. So we get this. We can get the value of x bar from those two equations if we equate these two, right? So x bar, integral of x times dA, right, divided by integral of dA. Right, so this gives us the x bar. Okay, now FR acts through at point C. Let's say this is point C, right? which is called the geometric center or centroid of the area under the loading curve, right? So that's a concept which we will learn in, I think, chapter 9, once we talk about the centroids of the areas. Okay, so no need to worry about this. All right, so this was the concept about the distributed loading and how to find the resultant force. All right, we'll understand more once we do these couple of problems. Okay, so problem 1. Now these are two beams given, one beam here, this guy, with a rectangular distributed loading on top with a magnitude of 400 pounds per feet, okay, which is W. Okay, and this is the second beam, which has a rectangular loading, right, with the maximum magnitude of 600 newtons per meter. Okay, and the length and everything is given. Now we will consider only rectangular and triangular loadings in this course, right? So we already know about the centroid of a rectangle and a triangle, right? And they are given in the inside back cover of your textbook also. So you can go through that and refresh your knowledge. Okay. What is the centroid of a rectangle? It's right in the center, right? Right here. What is the centroid of this triangle? Somewhere here, right? Somewhere here. So along the x-axis, it will be somewhere here, right? 2/3 of length from the base, from this point, and 1/3 from this point, right? From this point. So that gives you the location of centroid along x-axis, along the length. Okay. All right. So let's find out the resultant force, or we also call it concentrated load, right? So let's find out the resultant force or concentrated load due to this kind of loading. All right. So this first one, let's talk about this one. So we have this rectangular loading, and the magnitude is 400 pounds per feet. So what is the area? So let's say we are talking about the first figure, first case. So what is the area? Area is, we know what is the area, right? Area of a rectangle, length times width. Okay. So what is the width? Is the magnitude, right? This is the magnitude. This is the width, let's say. Okay. So 400 pounds per feet times, what is the length? 10 feet. So what do we get? 4,000 pounds. This is your FR. That's what we learned, right? That's what we derived, that to find out the resultant force, just find out the area. Okay, so this is your FR, 4,000 pounds, as shown here. Now we need to find the location of this resultant force, right? Concentrated load. This guy, or this point, right? How do we find that? We know that we are talking about a rectangle. So once we're talking about rectangle, then the location of the centroid is right in the center, right? So 10 by 2, we are at 5 feet. This guy is 5 feet, or X bar is 5 feet from this point. Okay, so that's how we are done with this first problem. Now let's talk about the second problem. What is the area of a triangle? What is the area? 1/2 times base times height, right? So in this case, we have 1/2 times base. What is the base? That's the length, right? 6 meters. Times height. Height is the magnitude. 600 newtons per meter. 600 newtons per meter. What do we get? Right? We get 1800 newtons. And that's your FR. Just find out the area, and that is your FR, right? So this is your FR, which is 1800 newtons. Okay, now just how to find out the location of this concentrated load, or location of the resultant force, this point. As we are talking about this triangle, so from the base of the triangle, what is the location of the centroid? You know it's 2/3, right? So 2/3 times 6. What do we get? We get 4 meters. Right? So that's how we can say that x bar equals 4 meters. Okay, so with this, I think we are able to learn something about these distributed forces and how to find out the resultant force, how to find out the concentrated load and its location. Okay, all right. Okay, now let's do another problem. This problem 2. We have a beam from A to point B, and we have some kind of loading, right? So we have a triangular load and a rectangular load, right, on the same beam. We have this triangular load and this rectangular load, right? The magnitude is 150 pounds per feet, the maximum magnitude, right? We have these dimensions, 6 feet and 8 feet. So this is given. What do we need to determine? The equivalent force and its location from point A. All right, so from point A, we need to find the resultant force or equivalent force, let's say FR, and its location, right? So X bar. How do we do this problem? First, the distributed loading can be divided into 2 parts, as we already discussed, one rectangular portion and one triangular portion. All right, okay, so let's say this is one portion, this is the other portion. Okay. Excuse me. Now find the resultant force FR and its location for each of the distributed loads. So each of these parts, right? Triangular part and the rectangular part. Now determine the overall FR of these resultant forces and its location. Okay. All right. So let's move forward. Now, as we said that let's take on them one by one. So let's talk about this. Let's talk about this triangular portion, right? This is the triangular portion. The maximum magnitude is 150 pounds per feet. All right. So let's say that we have FR1 is the resultant force of this triangular loading. Okay. So what is the value of FR1? What is the magnitude? We just need to find the area of this triangle, right? So 1/2 times base times height. So FR1 equals this guy, 1/2 times 150, which is the height, and 6 feet, which is the length, right? Or we can say the width. Right? So 6 feet times 150 pounds per feet times 1/2, which gives us 450 pounds as FR1. So this guy, FR1, is 450 pounds. This is the area of this triangle. All right. Now, what is the point of action of this FR1? Right. We need to find this distance. Right. This distance. Okay. So we know that from the base, from this point, from point A, it is 2/3 of the length. So 2/3 times 6. Right. Let's call it x1 bar. We are talking about FR1, so let's call it x1 bar. All right, so x1 bar equals 2/3 times 6. So we get 4 feet as x1 bar from point A, right? So this is your x1 bar. All right. Now let's talk about the rectangular portion. So let's say that FR2 is the resultant force of this rectangular portion, right? Rectangular part. So the loading is 150 pounds per feet. The length of this portion is 8 feet, right? So what is the area? Area is 150 pounds per feet times 8 feet. What do we get? We get this FR2 equals 150 times 8. We get 1200 pounds. So this guy is 1200 pounds. Just find the area of this rectangle, and that is your resultant force, right? Now we need to find this x2 bar, this guy, right? What is the point of action of this force FR2, right, on the beam? And from point A, because we'll be taking moment at point A, so let's take everything from point A, right? So from this point, we know what is the location, right? That is half of the length. So length is 8 feet. So from this point, this is 4 feet. So from point A, it will be 6 plus 4, right? So 10 feet. This is your x2 bar, right? So x2 bar is 10 feet from point A. Okay, so now we have these FR1 and FR2 and their location. All right, so let's move forward. Now the equivalent force and moment at A will be, so what is the total force? Total force is FR1 plus FR2, right? So let's call it FR, which will be 450 plus 1200. So it's 1650 pounds. So that's your total load or total force, FR1 plus FR2, right? Now let's take the moment of these two forces, FR1 and FR2, right? So FR1 and FR2, we know x1 bar and x2 bar. So just do force times distance, and that is your moment, right? So 4 times 450, this guy, and plus 10 times 1200, this guy. Now we are using this different sign convention with clockwise positive, right? So that's why we are taking these clockwise moments as positive. But again, we need to be consistent with this, right? So what do we get? We get 13,800 pounds feet as the total moment, right? Clockwise moment. Okay. Now we understand that FR is the total force, which is FR1 plus FR2, right? Now the moment due to FR equals the total moment due to FR1 and FR2, right? And this FR is at some distance from point A, let's say X bar, okay? So FR times X bar is the moment, total moment, which should equalize the moment from FR1 and FR2, which is 13,800 pounds feet, right? So just equate these two, FR times X bar, this guy, right, which is 1650 times X bar equals the moment created, the determined earlier, which is 13,800. Okay, so from here we can find out the value of X bar, which is 8.36 feet from point A, right, from this point. Okay, so that's how we are done with this from finding out the resultant force of the triangular portion and the rectangular portion, then finding out the total resultant force, which is FR, which was FR1 plus FR2, then going for the moments, finding out the moment of FR1 and FR2, which gives us the total moment, and then equating this to the moment of the resultant force FR. from there, we can find out the value of X bar, at which point the resultant force is acting on this beam. All right. Okay. So this last problem of today's lecture. Again, we have this beam. This is point O, right? And we have a moment acting 500 kilonewton meter at point O. Okay. Then we have these two triangular loadings with the maximum magnitude of 6 kilonewtons per meter. And we have a concentrated load acting at the right edge of the beam, 15 kilonewtons. Okay. The dimensions are given, 4.5 meters, 7.5 meters. All right, so distributed loading as shown on the beam. What do we need to determine? The equivalent force and couple moment acting at point O. Okay, so we need to find the resultant force or equivalent force, and we need to find the moment acting at point O. All right, let's move forward. Let's see how we do it. The distributed loading can be divided into two parts. We have two triangular portions, right? So we have two triangular parts. So just take them on one by one. Let's say this guy, number one, this guy, number two, right? So this is your first part. This is second part. Okay, so just take them on one by one and find the resultant force, and then find out the total resultant force if required. All right. Okay, let's move forward. Let's see how we do it. Okay, so let's take on this first part and find out the resultant force FR1. What is FR1? Just the area under the loading curve, right? So what is the area under the loading curve? That is the area of this triangle. So area of the triangle, 1/2 times base times height, right? So 1/2 times base, which is 7.5 meters, and 6 kilonewton per meter, which is the height, right? Which gives us FR1 as 22.5 kilonewtons, right? So now we have this FR1 of this first triangular portion. Now we need to find out X1 bar, right? This point. What is this point? Okay, line of the point of action of this force FR1. Okay, this is your X1 bar. What is X1 bar? As we're taking distance from the base of this triangle, so we know that it's 2/3 from here, right? So 2/3 of 7.5. 2/3 of 7.5, which give us 5 meters from point O, right? So X1 bar equals 5 meters from point O. All right. Now let's talk about this second section, second triangular portion, which gives us this FR2 as the resultant force. So again, we'll take the area of under the loading curve, which is the area of this triangle, right? So again, FR2 equals 1/2 times this 6 kilonewton per meter times 4.5 meters, right? Which will give us FR2 as 13.5 kilonewtons. Now we need to find out this X2 bar. What is X2 bar? Location of this force. This is your X2 bar. Again, let's take everything from point O, right? Okay, so X2 bar, we know that the location from this point is 1/3 of the base, right? So 1/3 of 4.5 meters. So 1/3 of 4.5 meters, and as we are talking about point O, so we need to add 7.5 meters, right? So 9 meters from point O is the location X2 bar, this guy. So this guy is 9 meters. Right, so now we have FR1, we have FR2, and we have their locations. Right, so FR1 and FR2. Okay, at 5 meters and at 9 meters. All right, so for the combined loading of the three forces, so we also have this 15 kilonewton force, right? So just add these three forces, so which will give us total force, FR. So 22.5 plus 13.5 plus 15. So we have 51 kilonewtons, which is the resultant force of these three forces, or all the forces acting on the speed, right? Now, what is the moment at point O? I just find out the moment due to all these forces. All right, so again, taking this sign convention, clockwise positive, what is the resultant moment about point O? 500 kilonewton meter, it's clockwise moment, right? It's clockwise moment, so it's positive. So positive 500, then 22.5 times 5, which is the moment due to FR1, right? So 22.5 times 5. It's a positive because it's clockwise moment. Moment due to FR2, 13.5 times 9, right? Again, clockwise moment, so take it as positive. Then the moment due to this 15 kilonewtons force, 12 times 15, right? 12 is the moment arm about point O, and 15 kilonewton is the force, right? Once we use the calculator, we'll get 914 kilonewton meter as the total moment. Okay, and that's what we were required to find here in this problem. All right, so with that, we come to end of today's lecture, and we are done with chapter 4 with this lecture. All right, thank you guys, and see you next time.